public lecture. Let me say that again. Welcome everybody to Aspen Center for Physics public lecture. I know your flyer said today the speaker will be introduced by Paul Gorbart. I'm taking his place. My name is Ali Yazdani, and I'm a professor of physics at Princeton University and also a member of the Aspen Center for Physics. And I have the great pleasure of introducing today's speaker, Cyrus Dreyer. So let me, before I get into introducing Cyrus, let me tell you that when he gives his talk, feel free to put comments in the chat, which I'll try to check. And of course, use the raise hand button when we go through his presentation. So Cyrus is a professor of physics at the Department of Physics and Astronomy at the Stonybrook University in the great state of New York. He's actually originally from rural Virginia. He did his undergraduate degree at the University of Virginia, where he studied physics and engineering. And he went on to graduate school at University of California at Santa Barbara, where he did his PhD in material science. He comes to physics from the area of materials, which brings a unique perspective, and you will see that today. He did his PhD studying semiconductors, in particular to their application to light-emitting diodes and how their properties can be enhanced depending on how you tune the material. Then he went on to be a postdoctoral scientist at Rutgers University in New Jersey, where he studied a range of phenomena, in particular how when you twist and flex a piece of material and how that twisting and flexing can generate electricity. He's a theoretical physicist and material physicist. And what he's going to tell us today, as you see from his great title, is trying to understand solids with supercomputers, not one electrons at a time, but many electrons at a time. And I think what is fair to say is that the understanding of solids has given us, of course, semiconductor industry and computers and now supercomputers. And what's fascinating, and we look forward to hearing from Cyrus today, is how we use these modern tools that we have gotten from understanding of solids to turn it around to understand more complicated materials, which are at the forefront of understanding of electrons' behavior in materials. So let us all welcome Cyrus. And again, I remind you to feel free to use the chat function and your raised hand, and I'll mute myself now and turn the floor to Cyrus. Welcome, Cyrus.
Thanks, Ali, for the introduction, and thanks everyone for tuning in. I really wish I could be in front of you in person, but I guess this is the next best thing. So if you look behind me, you see a lot of books. I'm actually in the Beta Library at the Aspen Center for Physics. So just really happy to be in Aspen, and I hope that we can be in person quite soon. I'd like to start my talk with a really fundamental question, and that is the question of what is the most important concept in all of science? So if you ask 100 different scientists this question, you will probably get 100 different answers. Since it's my talk, I will give you my favorite answer to this question. And that answer was given by a famous physicist, Richard Feynman. Richard Feynman revolutionized many areas of physics. He got a Nobel Prize in 1965. And he was quoted as saying that if by some cataclysm, all of scientific knowledge was destroyed, and we could only pass one concept down to whatever beings were replacing us so that they could rebuild all the scientific knowledge that we know, that concept would be the atomic hypothesis that all things, everything we see around us, are made of atoms. And he went on to say that atoms are little particles that move around in perpetual motion. They attract each other when they're a little distance apart, but repel each other when they're kind of squeezed into one another. So I agree with Richard Feynman. I think this is the most important concept in all of science. And throughout this talk, we'll kind of be unpacking this concept of all things made of atoms. So what is an atom? Well, this is kind of how I picture an atom. It's a cartoon picture. Atoms are made up of subatomic particles, kind of by definition. We have, in the middle of the atom, we have protons and neutrons. Then the rest of the atom is made up of electrons. Some of them are quite tightly bound to those protons and neutrons. Other of them are more loosely bound. We call those valence electrons, and we'll come back to this concept a little bit later in the talk. So there are many different types of atoms. We arrange atoms by how many protons, neutrons, and electrons they have, and we put them into what's called the periodic table of the elements. So you've probably seen this table. Maybe it takes you all the way back to high school chemistry, and maybe at some point you even understood why all of these elements were arranged in this way. For the purposes of this talk, it's not that important, but what is important is what Richard Feynman told us, and that is that all of the things that we see around us are made of these atoms in the periodic table. So it's a pretty obvious statement that there are a lot of different things with a lot of different properties that we see around us. So if I look out the window, I see some aspen trees and other plants and grass. If I was a little higher up, I could probably see some rocks and see the maroon bells and the mountains. I wish I could see a lot of humans in the room, but I'll have to see them digitally through Zoom. But animals, stars, planets, et cetera, all of these things are made of atoms. So of course, this is kind of a basic concept in science and is not too surprising to most people. But when you stop and think about it, it's kind of fascinating because there really aren't that many types of atoms. So if we look on the periodic table, which contains all of the atoms that have been, or all of the elements that have been fabricated or have been measured or detected, there are only about 118 elements, and many of those are rare or not very stable. So actually all of this vast properties of things that we see around us come from a very small subset of these elements. So an obvious statement is that there are way more things with way more properties than there are elements in the periodic table. So how do all of these things get built out of such a small toolkit? Well, one reason is, of course, that things aren't just made out of one type of element. So giving an example of a human, we're made out of a huge number of different types of elements: oxygen, carbon, hydrogen, nitrogen, calcium, other metals, et cetera, But even very simple objects, let's take just a chunk of metal, not just any chunk of metal, but a chunk of metal taken from a turbine blade of a jet aircraft. Even though it just looks like a gray piece of metal, it contains a ton of different types of elements, including niobium, tungsten, aluminum, carbon, vanadium, molybdenum, many that you may not even have ever heard of. So that's one reason why we can go from not that many atoms to a lot of different things that we see around us. But that's not the only reason. We can see that that's not the only reason by a simple example, by considering two different substances, diamond on one side and graphite on the other side. So diamond and graphite are both made of carbon, basically just carbon. But we know from our everyday experience that they have very different properties. So diamond is shiny, so we put it in jewelry. It's hard, so we use it to cut and drill through other hard things. And graphite is not shiny, and it's very soft. That's why we use it in pencil lead, because when we move our pencil along a piece of paper, some of the graphite breaks off and is left there, and therefore we can write. So in this case, we can't explain these two very different properties by different combinations of elements. And so in general, this is a pretty complicated question, and a question that takes up a large area of science, is how do we go from all of those little atoms on the periodic table to all of the vast array of things that we see around us: plants, animals, trees, pieces of metal, rocks, etc. And so, like I said, this is a big question in science. I'll try to sharpen this question a little bit and break it up into three parts based on what we've just seen. So one big question is, what combinations of elements give us things with different properties? We already saw that because we can combine all kinds of elements together, we can get a variety of different things. And what are the details of how that works? Why can the same element result in objects and things and substances of different properties, like the case of diamond and graphite? And then finally, Ali alluded to this a little bit earlier. Can we predict and engineer the properties of different combinations of elements in order to make turbine blades with the properties that we want, or drugs that attack the pathogens that we need, and so on and so forth? So these are the big questions that I will be addressing in this talk. And also, as Ali mentioned, I have kind of a few different perspectives in my mind on these questions. And in general, in science, there's a few different perspectives. So at the risk of overgeneralizing, I would say that the physics perspective to answer these big questions is to really start from the basic principles of how atoms interact and then build up from there to try to figure out how those atoms combine together to give us all these things. What I'll call the chemistry perspective is a little bit different. It would be more along the lines of developing empirical rules that describe how different elements combine together and give us different properties. And then finally, if I were to put on my material science hat or my engineer's hat, I would be more interested in characterizing how atomic structure and processing allow the properties of materials to be engineered. But of course, we're in the Aspen Center, or I'm in the Aspen Center for Physics. And so in this talk, we're going to really focus on the physics perspective. We're going to start at the most basic level of how atoms interact, and we're going to build up from there to answer those big questions that I had on the previous slide. Okay, so to start our journey, let's go back to Richard Feynman. So Richard Feynman basically already told us what we want to know. He told us the basic principles of how atoms interact. They attract each other when they're a little distance apart, and then they repel each other when we squeeze them together. So this is really at the heart, of course, of how we go from atoms to things, is how these atoms bond together. Because again, these atoms are very tiny. The things we see around us can be very large. And so we need to combine a lot of atoms together in order to create them. And so the way that atoms bond together, as kind of shown in this cartoon picture, is via those loosely bound valence electrons that I mentioned near the beginning of the talk. So really, if we want to take the physics perspective, we want to start at the most basic level and understand how atoms bond together, then we really need to understand how these valence electrons interact with each other. And when we take two atoms and we put them together, how those valence electrons cause them to stick together or not. Okay, so we've taken kind of one step back from atoms, and we've taken that step to electrons. So from the physics perspective, we want to know how electrons interact. And in order to know that, we need to answer basically three questions. First of all, what is an electron? Second of all, what are the basic principles of how electrons interact with each other? And then finally, third, which is basically encapsulating all the big questions I mentioned earlier, how can we go from those basic principles from the first two questions, about electrons and how they interact, to predict, engineer, understand the properties of complex things? Okay, but let's start at the beginning. So what is an electron? So I'm not going to answer that question about what is an electron. Instead, I'll answer a slightly adjacent question. I'll answer how we think about electrons. Because physicists have this kind of two minds when we think about electrons. So I said an electron was a subatomic particle, and at least for me, if I think in my mind of a subatomic particle, I picture a tiny little billiard ball that is zipping around in space. And actually, electrons have a lot of a lot of properties that can be understood by picturing them as little billiard balls zipping around in space. But unfortunately, there's this other side of our physics minds when it comes to electrons. And that is that electrons also have a lot of properties that are not similar to particles, but are more similar to waves. And by waves, I just mean things like ripples on Maroon Lake if you were to throw a pebble into the water. And so we keep these, as physicists, we keep these both of these pictures in our mind, that electrons have properties of both particles and waves. And if this sounds strange, don't worry, we'll come back to it in a few slides. So just for the time being, in order to remind you that even though I'll draw these little billiard balls, that they actually have some additional properties, I'll draw as a cartoon picture these little wave packets on all of the electrons in the following slides. Okay, so let's take our two atoms and let's put some electrons in those electron clouds. So the gray clouds that I said were the valence electrons, now we have little particle wave things that are zipping around in there. So there's another thing that we know about electrons, something that you also probably knew at some point, and you could probably guess from the name, and that is that electrons carry electrical charge. So we know in great detail what this electrical charge is based on the work of physicists like J.J. Thomson and Robert Millikan, again, both Nobel Prize winners. And what we know is that electrons carry negative charge. And when we look at atoms, if we look at the nucleus with the protons, they have positive charge. So we have negative charge and positive charge making up these atoms. So I think I'll just leave the first question at that for now. Again, I haven't really said what an electron is, and I probably won't in the talk, but I've said how we think about it. It's a subatomic particle wave thing, and it carries negative electrical charge. So let's move on to question number 2. What are the basic principles of how electrons interact with each other? Well, we know how charged particles interact with each other. So if we have two charged particles with opposite charge, it's just like having a north and south pole of a magnet, they attract each other. And the closer they get, the more they attract. And if we have like charges, say two negative charges, that's just like having two north poles of a magnet, and they repel. And the closer they get together, the more they repel. And so because in atoms, as I said before, we have these negative and positive quantities, these negative electrons, positive nuclei, really a lot of the interactions are based on this idea that like charges interact, like charges repel and opposite charges attract. And we can write down there the energy as the charge, the two charges divided by their distance. Okay, so we also have some other things that are going on in the atoms. So all of those negative charges would like to be very close to the positive charges, but they can't be. And one of the reasons why they can't be is that they also have some kinetic energy. So they're zipping around. I always talk about electrons zipping around, and because they're moving, they have some kinetic energy. Okay, so are we done with the second question already? We're moving extremely fast. Well, not quite, because all of the things that I just told you, the fact that electrons can interact with their charges and they are zipping around, so they have kinetic energy, those are all consistent with electrons being tiny little charged billiard balls. And I mentioned again before that we can't just think about electrons as tiny little billiard balls. We have to take into account this weird wave nature of electrons. So how do we do that? What are the implications of that? Well, the implications of that is that we need to understand electrons through the lens of a field of physics known as quantum mechanics. And one of the founding fathers of quantum mechanics who really taught us how to understand particles like electrons in terms of waves was Max Born. He was another of these famous physicists that revolutionized many different areas of physics. He got his Nobel Prize in 1954. But there is actually, Max Born has a claim to fame that many people, including physicists, don't know of. He was actually instrumental in making the critically acclaimed musical film Grease, which you may remember. So Grease came out several years after Max Born died, so he wasn't actually directly involved with the making of the film. He has nothing to do with John Travolta, but he's actually Olivia Newton-John's grandfather. So you can look that up. It's true, and impress your friends with some trivia. Okay, but back to quantum mechanics. So how can we understand quantum mechanics? Well, let's go back to our guru, Richard Feynman. And Richard Feynman was quoted as saying, I think I can safely say that nobody understands quantum mechanics. So we're not off to a very good start, because Richard Feynman is a famous physicist, and if he thinks no one understands quantum mechanics, then probably no one understands quantum mechanics. But let's take a step back from quantum mechanics and just think about waves. So waves are something that's pretty familiar to all of us. We see them all over the place. So of course, the number one place you might think is in the water, as I mentioned before. Also, we know light to act as a wave with different colors. And you can hear me because my voice is causing vibrations in the air, which is causing sound waves. Unfortunately, it has to go through a computer to get to you, but that's another type of wave that we're very, very familiar with. And so we're very familiar with waves, both at the intuitive level and also at the scientific level. And that really helps us understand how to understand electrons. Okay, so these are more complicated waves, water waves, sound waves, light waves. Let's break it down again with the physics perspective in mind. Let's break it down to the most simple wave that we can think of. And so here is a very simple wave. It's just a line that is oscillating. You could think of it as a guitar string or something like that. I label that it is oscillating somehow in space, and it could also be oscillating in time. And the way that engineers and physicists think about waves is in terms of these quantities we call wave functions. And so a wave function, you don't have to worry about specifically what it is, but it basically describes, it encapsulates all of the properties of a given wave. So that will include its wavelength, the wavelength of the wave, the amplitude or the height of the wave, where the wave is in space, as I put x, and then what is happening with the wave in time. So we also have t. So it turns out that we use the exact same quantities to describe electrons in this context. We write down the wave function of the electron. It's usually written down with the Greek letter psi. And this wave function depends on the position of the electron. It depends on time. And it basically tells us all of the information that we need to know how electrons interact, how atoms bond together, and to make a step towards answering those big questions that I posed at the beginning of the talk. So if we go back to that situation where we have our two atoms, they're attracting each other like Richard Feynman told us they would. They have a lot of electrons zipping around. What we would like to do in order to understand this is to write down a wave function for this system. And so now we have a lot of electrons. And so we have a lot of positions of electrons that we need to keep track of. And then, of course, they're zipping around. So we have a wave function that depends on time. So this is basically what we need to solve in order to understand how electrons interact. So how do we solve this wave function? Well, thankfully, we've been told how to solve the wave function by another famous physicist, Erwin Schrödinger. Erwin Schrödinger got his Nobel Prize in 1933. And he got his Nobel Prize in part for the equation that takes his name, the Schrödinger equation. So I'll put the Schrödinger equation up on this slide. It's a little bit complicated. There's a lot of symbols and a lot of other weird stuff going on. We can identify those psi's, those wave functions, that are in there. So at least that's a little familiar. And what I would argue is that even though this equation looks very complicated, and I would ask you not to worry about what all the symbols mean, it's actually pretty simple and kind of beautifully simple. And I can illustrate that by walking through what all of the contributions to this equation correspond to. They're all things that we have seen earlier in the talk. So this first term in the equation, that's the kinetic energy. So again, electrons zipping around, they have kinetic energy. That is a term in the Schrödinger equation. That's something we need to know in order to understand the electrons. Then we have some attraction between the electron and the ion. Again, they're different charges, they attract each other. That's another thing that we need to know if we want to understand the electrons and the electron wave function. We also have electron-electron repulsion. They're like charges, they repel each other. And then finally, we have ion-ion repulsion. So we have these two nuclei, they're positively charged. And as Richard Feynman told us, if we bring the atoms too close together, they repel. That's because these nuclei are like charges and they repel. So that's basically it. So that's all that goes into this equation. So even though there's a lot of symbols, conceptually, it's fairly simple and kind of beautiful. And especially because, again, taking the physics perspective, it lays at the foundation of how we can understand how atoms bond together to give us a huge variety of things. So if you were to ask Erwin Schrödinger what he thought of the equation, he's not as excited about it as I am. He actually said, I don't like it, and I'm sorry I had anything to do with it. But we're not going to let Erwin Schrödinger's negativity derail us. Let's try to get a more positive perspective on where we are so far in our understanding. And so from that, it will come from another famous physicist, Paul Dirac, also Nobel Prize winner. And what he said about the Schrödinger equation and quantum mechanics is that he was excited about it, at least for right now. The underlying physical law is necessary for the theory of a large part of physics, and all of chemistry are now completely known. So that's great. We've answered question number 2. So we know how electrons interact. They interact through electrical charge particle interactions with kinetic energy. We can understand their wave-like nature through these kind of weird objects called wave functions within the framework of quantum mechanics. Okay, so moving right along, let's now answer question number 3. And question number 3 will get us to our big questions of how atoms combine together and form all of the variety of things we see around us. Okay, so let's go back to Paul Dirac. Unfortunately, there's a second part of his quote. And the second part of his quote says that even though the underlying physical laws are known, exact application of these laws leads to equations that are much too complicated to solve. So it sounds like Paul Dirac and I are at odds on this point. I just tried to convince you that the Schrödinger equation is very simple. It just contains these simple electrical interactions. So of course, I'm not contradicting Paul Dirac. He has a Nobel Prize and I don't, at least yet. And the reason why Paul Dirac tells us that these equations are too complicated to be solved is just the fact that electrons are very small, and there are a lot of electrons in even the simplest object that we would try to describe. So I can explain it kind of pictorially in this way. So say we have just a couple of electrons, just 3 electrons. So we know that they're like charges, they repel. So we have to keep track of the repulsion between, mutual repulsion between all of these electrons. Now let's add a few more electrons. Now all of a sudden it's getting a little complicated. We have a lot of lines here. We need to make sure that we keep track of this electron repelling this electron, which repels this electron, which repels that electron, et cetera, et cetera. And even just adding a few more electrons, now it's really a mess. There are lines everywhere, and we're trying to have to keep track of so many electron repulsions. And so if we want to describe even a very simple system, say 1 gram of graphite, again, just carbon, it contains way more electrons, a huge number of electrons, something like what I wrote down here, which is actually about the number of stars in the universe. So this is a huge problem, right? We can never draw all the arrows necessary to take into account all of the electron-electron repulsions that is in even the simplest system, a gram of carbon. And actually, this is kind of at the heart of why we can have very simple building blocks, atoms and electrons, result in such a wide variety of properties of materials or things, people, planets, stars, plants, etc. It's because that when you put a lot of electrons together and you take into account all of these different interactions, then you get a lot of interesting properties. And if you were to try to break down all these electron interactions into kind of smaller parts, then you would a lot of times lose the complexity that gave you all of those exciting properties in the first place. Okay, so that's basically why in my title, I said that when we want to understand solids, when we want to understand things, the things we see around us, we have to do it many electrons at a time. We can't just consider one electron at a time. So there's another part of my title that I haven't talked about yet, and that is supercomputers. So you may be thinking that why do I need to draw arrows on the slide to take into account all of the electron-electron interactions in a complicated system? We have massive computers, really huge computers all over the world, and we can just take this problem and we can put it on a big computer, and the computer can keep track of all of the electron-electron interactions and tell us the answer. And unfortunately, if we try to do that, it doesn't really get us that far. So the biggest computers in the world can handle something of about 50 electrons. And so I don't know if you remember the number that I showed you a few slides ago of how many electrons are in a gram of carbon, but it's way more than 50 electrons. So why we have really powerful computers? Why can't our computers handle more than just a few handfuls of electrons? Well, it turns out that the difficulty in keeping track of all these electrons, it scales really poorly as we accumulate a number of electrons together. So this kind of simple few electrons, I can actually solve for all of the properties I need, solve for that wave function, if you remember earlier in the talk, on my laptop. But by the time I get to the biggest computers that are on Earth, because this difficulty increases so quickly, I've only gotten to about 50 electrons. And there are some things that we can understand by just understanding 50 electrons, but we would like to do a whole lot more. So how do we proceed? Are we stuck? Well, let's go back again to Paul Dirac, and there was actually a third part of that quote that I put up. And the way that Dirac told us to proceed is that we need to find approximate practical methods to determine the properties of electrons via quantum mechanics. And in that way, through approximate practical methods, we can hopefully determine the features of complex systems. So that's really the answer to the third question. How do we go from these basic principles of how electrons and therefore atoms interact to the properties of very complex things like we see around us? We need approximate practical methods, as Dirac said. So a lot of areas of physics have been focused on just that, developing approximate practical methods. And I'm going to tell you about one approximate practical method. It's actually one of the most successful of all of the methods in condensed matter physics. It's my favorite because my research is based on it, but I think it's fair to say. So in order to describe this method, let's go back to our interacting system of many electrons and this whole mess of arrows that I showed before. So what the method that I'm about to tell you about, the way it works is basically we select one electron out of all of those interactions, and then we just smear out, we blur our eyes and smear out the interaction of all of the other electrons. And it turns out that if we do this procedure, we can determine the interaction between one electron and all of its smeared out neighboring electrons. And the approximate practical method that I will tell you about, known as density functional theory, basically does that for each electron in turn. We select an electron out, we smear out all of the other electrons into some background, we calculate the interaction between that one electron and the background, and then we move on to the next electron in our system, and then the next one, and the next one, and the next one. So this theory, density functional theory, or DFT, it was developed by another famous physicist, Walter Kohn, who wrote this very innocuous sounding paper called the inhomogeneous electron gas, which really laid the theoretical framework for this idea of density functional theory. So he got his Nobel Prize in 1998, but his Nobel Prize has an asterisk next to it because it was actually a Nobel Prize in chemistry. And he was famously disappointed that he didn't actually get the Nobel Prize in physics. So I apologize if there are any chemists in the audience. Okay, but why is density functional theory so useful? It's really useful because we can take this general concept of one electron smearing out the rest, and we can put it on those same computers that have failed us earlier. And those computers do a lot better at this problem than they did at the exact problem of all the electrons interacting. So basically, we can get to way more electrons. And because we can get to way more electrons, we can treat way more interesting systems. So we can't go to maybe the number of electrons that I wrote down before, but we can really make some progress on understanding how atoms bond together, and then hopefully how we can get all of these amazing things that we see around us. So using concepts like density functional theory, we can determine why diamonds are hard and shiny, and why graphite is soft and not shiny. We can understand, in that case, that the atoms bond together in different geometries. If you're interested in the details, you can ask me after the talk. We can engineer the properties of things like turbine blades of aircraft so that we can fly across the country. We can understand the properties of molecules that maybe we can use in drugs, and even some biological systems. So we can't use DFT to understand all the properties of a lion, but maybe some very, very simple biological systems we can treat. So that's basically the answer to question 3. The way that we go from these basic principles to the understanding the properties of complex things is through these approximate practical methods. And one of those approximate practical methods is density functional theory. So in the last few minutes of the talk, I'd like to just give you some kind of random examples of some of the things we can use density functional theory to understand. And so these examples are random, and unfortunately, Ali blew my cover telling everyone what I worked on. You might recognize them as some of the things that I work on. So I work on them. I think they're the most interesting. And so I'll describe them a little bit to you, and maybe you think the same. Okay, so if we take a very simple material, it's a very simple solid, and we really zoom in to that solid and we look at it, what we will often see is, if we zoom in enough, that the atoms are arranged in a fairly regular order. So we would say that forms a crystal. So it may have different types of atoms, as indicated by these blue and red spheres, but they're all ordered in a really nice pattern. But if we were to pull back just even a little bit, we would see that no matter how nice the pattern is in certain spots, in other spots, we have some imperfections. And these imperfections can be really, really tiny. They can be on the size of one atom. They could be maybe an atom that's missing, that's supposed to be there in this regular order of atoms. They can be extra atoms that are not even supposed to be in this material. There can be impurities. Or maybe an atom is in the wrong place in the crystal. And so it turns out that the properties of these tiny point-like defects is really fascinating. So even though they're very small compared to the microscopic material, they can completely alter the properties of that material, and they can have really real-world consequences. So I'll tell you about two such consequences. One is a problem that's very near to my heart. It's that of lighting. So you have probably seen in the last couple decades that there has been a revolution in lighting. So before you could choose between an incandescent and a fluorescent bulb, and now there's these new bulbs called light emitting diodes that everyone's telling you are very energy efficient and they last a long time and they're really great. And so if you look at a light bulb, an LED light bulb, it has these tiny little electrical devices in them called LEDs. And we can make LEDs that emit at all kinds of different colors. And if we now zoom in, not just to the bulb, but to the actual LED, then it looks a little bit complicated and messy. So I won't expect you to kind of understand the schematic so well, but basically it is a sandwich of two different types of materials. And where the two materials meet at the kind of middle of that sandwich, we excite electrons into really excited states. So they have a lot of kinetic energy moving around. And then when they relax down, they emit some light. That's indicated by these blue splotches. And so that's kind of how an LED works. Sandwich of materials, the sandwich of materials excites some electrons and they emit. So it turns out that if you have those tiny microscopic defects in your sandwich, those defects will be really bad for this process. They will capture those excited electrons and not emit any light from the material. And so if you do all the work to excite an electron and then it doesn't emit any light, then you've hurt the efficiency of your device. And so it turns out this is a big problem, kind of an ongoing problem. LEDs are very efficient, but to make them more efficient, what we really need to know are what type of defect is limiting their efficiency via this process. And so we can use density functional theory to not just look at ideal solids, but also to look at those little defects. And we can calculate things like how the efficiency would decrease for different colors of LEDs. And hopefully then we can go to our experimental colleagues or even our colleagues in industry and tell them that they need to avoid these certain types of defects when they make their LEDs, and we can get even more efficient light bulbs. So that's one kind of random thing that you can do with DFT. I'll give you one other one. Again, Ali introduced this. And that is another useful, before I get away from defects, I just wanted to say that defects often get a bad name because defect kind of sounds like something bad, but defects can be good. For example, in diamond that we've talked about throughout this talk, defects can give color to different pieces of diamond. The defects that give the diamond color are called color centers. And actually, you can use color setters in diamond to make new types of electronics, type of electronics called quantum computers. So I'm not going to go into the details of how you can do that. If you're interested, you can ask me after the talk. But it's amazing that something that you would think is maybe a bad thing, an imperfection in a crystal, can be used for new and exciting technology. So the last example that I'll give is another example from my research, and it's looking at what happens to materials when we deform them, when we squeeze them, when we twist them, when we pull on them, etc. So here the material is I've just depicted it cartoonishly like a little grid. And with some materials, they're called piezoelectrics, if you pull the material apart, you can actually generate a voltage. And you can use that voltage to power a little light bulb, hopefully an LED light bulb. And so this is a very useful concept because we can transform electrical power to mechanical work, or we can transfer mechanical work to electrical power and back and forth. And so you have some piezoelectric materials in your phone and in various other devices. But one of the things about piezoelectrics is it's only very specific materials that have this property. But it turns out that if you apply very specific deformations, then actually all materials can turn a mechanical deformation into a voltage. And specifically, if you were to take some material and you were to bend it, actually take any material and bend it, that material would generate a voltage. It might be very, very small. You'd have to bend it a lot and you'd probably break it, but it's still a universal thing that we can measure in the lab. And so this is a property called flexoelectricity. It is, again, measurable in the lab. Our experimental colleagues can make tiny little pieces of material, and then they can bend them and they can measure this voltage. And as you might expect, the fact that this happens in any material would be very useful for electronics and other applications. And so there's kind of an ongoing search about how to find materials where we can actually take advantage of this property. And this is where DFT, density functional theory, comes in. We can explore this property in a lot of different materials and hopefully find some that are useful for electronics. So anyway, through those random examples and through all of the other discussion that we've had in this talk, I hope I've convinced you that we can use supercomputers to understand all of this wide variety of things that we see out there with our approximate practical methods, starting just many electrons at a time. So thanks for your attention, and I'll take any questions.
Well, thank you very much, Cyrus. We give you a virtual clap here for that excellent talk. And thank you for finishing in time to have some questions. So let me just remind everyone, you can use the raised hand or type your question in the chat, whichever you prefer. And it looks like we already have one question from KD, which asks, microscopic defect in materials with sequential results sounds a lot like point mutation in viral RNA. Can you control this for LED applications?
Yeah. So there is definitely a parallel between point-like defects in LEDs and kind of defects in your DNA or RNA. The fact that even a very small change can cause a very big difference. It's definitely an interesting idea to try to use the same concepts that people have been using in biology and maybe have some tiny little robot viral RNA that can fix the defects in LEDs. I would think that it's probably much more commercially practical to try to remove those defects when you're actually constructing the LED. So changing how you put those sandwich of materials together to hopefully get more perfect materials. But it is a cool idea we can think about.
Okay, very nice. So we have a couple of more questions. I go to Connor Hoffman. Connor, do you know how to unmute yourself?
Yes.
Go ahead, please.
So I'm curious if you've had any, or if you've even tried using this on superconductors to try to predict the properties of different materials on that.
That's a great question. So superconductors are really, really difficult for this particular approximate practical method, DFT, that I talked about. And it's really because one of the things that gives us superconductivity are these specific interactions between electrons. And so a lot of times, if you do this kind of smearing out process, you lose those strong interactions, strong correlations between electrons that that kind of gives you the superconductivity. But
So
with
by
that being said,
sorry, go ahead.
oh yeah, sorry. I don't want it to be too negative. We can actually calculate a lot of properties of materials before they become superconducting. So properties of kind of the host material before it's cooled down to be superconducting that may tell us whether that material will be a good superconductor. And actually some of the newest batch of superconductors that are now, hovering around room temperature, whatever you call it, they partially came from some predictions from DFT-like theory.
Okay, so you can predict other properties other than superconductivity that might help you predict if it would be a good superconductor.
Exactly.
Gotcha.
Very nice. And we have one more question from Catherine Porter. Catherine, could you unmute yourself?
Yes, thank you very much. I actually had two questions. One was, why did Schrödinger not like his equation? That's one. And the other, and I am not a scientist, so I'm just a lay person, but what industries are currently using some of the things you talked about to make products, or, in sort of the practical sense? Anyway, that's that. Thank you.
Yep. Thank you for your question. So in terms of the first question, so I'm not a science historian, so I might get myself in trouble by speculating, but I mean, quantum mechanics is weird, and it's one of those things that when you don't understand it, it seems weird, and then when you understand it a little bit, it seems normal, and then when you understand it a lot, like Erwin Schrödinger does, it seems weird again. And I think a lot of the founders of quantum mechanics were very uncomfortable with how weird it was when you really understand the details. So I won't say anything more than that, but your second question is definitely an interesting one. How these concepts affect industries. And so there's a pretty wide variety of industries that are more and more starting to use these types of calculations for things that are useful. So for example, in chemical engineering contexts, where oftentimes you're trying to take one chemical and create another more useful chemical out of it. A lot of that has to do with how that chemical binds to certain materials. And that's something that you can learn a lot about from techniques like this. Also in the semiconductor industry, so the materials that go into our phones and computers and things like that, now those devices are so small that we really need to understand them from the atomistic level using these types of techniques to know what's going on, to know if some new concept will work. So those are just kind of two examples. And a lot of my colleagues from grad school have gone in those and other directions in industry and made a lot of money. So, yeah.
Very good. So we have one more question from Mark Alford, which is typed on chat. You said that brute force methods only work up to about 50 electrons. Is there an upper limit on the size of a system that can be treated by DFT?
Yeah, that's a great question. So it's a very active area of research, and the limit is being pushed all the time. So I would say that that now DFT calculations can handle thousands or tens of thousands of electrons, and so, or yeah, on order. So that might actually not seem like that many when you think about that number that I put up on my slide for a gram of carbon. But we can also take advantage of things like that I mentioned, that oftentimes when you zoom into a substance, it has a very ordered structure. So if we know how some of it interacts, then we can kind of scale that up, knowing that it's ordered, and figure out how a much bigger system might interact.
Very good. Excellent. And let's see. I just want to make sure if there are no more further questions. Looks like thanks for everyone for staying. Oh, we have one more. Katie has another comment. Really well done and said above regarding the presentation. Please do correct a few things before your Nobel nomination. You even
Thanks,
got
Katie.
some feedback on your slides.
Yeah.
I think if there are no further questions and comments, let us all thank Cyrus again. And thanks for everyone for staying through the question section. And we look forward to seeing you at another Aspen Center for Physics public lecture. Thank you and goodbye.